So today we are going to talk about end-to-end tests. So I need to apologize, there's no AI, okay? It's all about our own story from ID to production. How we built infra to run serverless browsers at scale at weeks. But stick with me until the end, because lessons do apply to AI at the end. So for those who don't know me, I am David, lead software engineer at Wix for the last 2 years. Yeah. I was born in Paris, and I have 3 daughters, Baruch Hashem, because it's way better than boys, to be honest. I've learned also to stay calm under chaos. So, yeah. So now, guys, let me give you some context. We run more than 2.5 million of end-to-end tests every single day across hundreds of PR. And that's not a typo. 2.5 million of end-to-end test execution. End-to-end tests are critical, especially now when AI generates more and more of our code. We need to make sure that the code actually works, right? So guys, we built SLED, which is the Wix end-to-end testing platform. Our mission rests on 3 pillars. We'll start by velocity. Tests need to run fast. A developer waiting 2 hours for a green build is a developer who is blocked. And that's exactly the opposite of what we want. The second pillar is debugging experience. When test fails, developers need to understand why and quickly. So we provide things like flakiness analysis, local reproduction, and repairing failures. And the third pillar is Wix integrations. Our end-to-end tests need to do Wix-specific stuff, like cloning a production site, assigning it to a premium account, or also work as an authenticated user. This is deep integration with Wix's own system. But here's the core tension we had to deal with. Velocity means parallelism, running hundreds of tests in parallel. But parallelism means infra. Infra costs money, guys. So these 2 concerns pull in opposite directions. Our job was to find the right balance. Not 6, 7, yeah. 1 year ago, we were running all of our end-to-end tests in AWS Lambda, guys. Yeah, in AWS Lambda. Why? Each spec file got its own Lambda, running hundreds of tests inside Lambdas. So they were all firing at once. So velocity-wise, it was amazing, guys. Yeah, great parallelism. But then our FinOps team called us, dude, what the hell? Costs are becoming exponential. The Lambda approach was built for a much smaller scale than what we have today. We were paying too much, and it was only going to get worse. So we needed to stop reinventing the wheel, and let's start at looking at industry standard. How we run end-to-end tests in the world, yeah? So let's start from scratch with the right tool. And yeah, the answer was Playwright, right there on the screen. Better developer experience, multi-browser support, faster and more reliable. And guys, built to handle flaky tests. So at the moment, we even ask ourselves, do we even need SLED? So before we can answer to that question, we need to understand how Playwright works in CI. There is a spec file here in the CI machine. Playwright needs to execute it. Before executing it, it will just download a browser, yeah, and it will start to connect via a WebSocket connection, localhost. Everything is fine. A direct and persistent line of communication. So as long as that connection stays open, the test sends command to that browser. So if in the spec file we have some commands like navigate, set cookies, on a click button, on anything, we are sending all of those instructions to the browser. Everything is fine. But yeah, that's the problem. When we have more than 500 spec files per pull request. So the question becomes, how do you actually run all of those tests in a PR without blocking developers? So we have two obvious options. The first one, yeah, go sequential. I mean, one test at a time, one browser, one connection. It's clean, but it will take hours per PR. That's not acceptable. A reminder, we have speed and growth. We need to be very fast. But the other option was not good as well. Go parallel, launch 50 WebSocket connections. But then what happens? Machine crash. The browser isn't built to run 50 sessions into one box. So we understand from this that Playwright alone doesn't give us the velocity that we at Wix need. So what are we doing? And the answer was, let's host the browser out of CI machines. Why not? At the end, if you can't have high parallelization in CI machine, host the browser somewhere else. Somewhere we have real control. And that's exactly where SLED become essentials again. So that's the new architecture. CI machine run Playwright. There's no browsers anymore. Instead, Playwright will connect to our SLED platform. We control the browsers, the connection, there is a clean separation. But now that we took the responsibility of hosting those browsers, we need to understand who are we dealing with. Because browsers, there are no like web servers. They are memory intensive. They're unpredictable. And then can crash in mysterious ways. We were dealing with a dragon. And we had to learn how to train it. An example that really surprised us. One single WebSocket connection, just one, can cause a memory spike big enough to crash the entire browser. One connection, one tab, the whole thing goes down. Basically, you can just generate a whole DOM, you put it inside your browsers, and then the memory is just crashing. HTTP servers don't behave like that. So we had to set a hard constraint, the maximum 4 connections per browser pod. Non-negotiable. Stability before sophistication, because if you can't trust the browser to stay alive, so nothing else will matter. And we had to make an assumption, guys. We didn't know how to verify it. 1 gigabyte per connection, roughly. This is our assumption. In Playwright docs, they are saying the same. OK, so 4 connection, 4 gigabyte, that gave us a model to work with. But remember this assumption, it will come back later. So that's the architecture we built. On the right, you can see serverless browsers. 2 browser pods in this example, managed by Kubernetes, for those who are understanding. Each pod has 4 gigabytes of memory on 4 connection slots. And in the middle, you can see the proxy. The proxy will play a very important role, you will see, in the future. A PR comes, OK, I have 2 WebSocket connections, and you need to find me a slot. So the proxy will use round robin and will distribute the connection in a fair way. So far, so good. Same with another PR, same distribution on each browser. And then the last PR is also filling all the remaining slots. And now I'm asking a question. Imagine this is the current browsers, they are all full. And now there is a 4th PR coming on. So I'm asking a question. Are we going to drop the next connection? Is it something we can do? They're all full. We cannot do anything else. That's not possible. So let me introduce you to the proxy king. The proxy king, it's our custom-built proxy because no existing solution gave us what we really, really needed. We need full control over our traffic. So to train your dragon, you need a king, this one. What we'll do? Let's see. This is the 4th PR coming up. Then we stream our connections. So normally this would be dropped, but the proxy king will put them in a queue. The waiting connections sit right there. And the test runners doesn't even know that there is a queue. From Playwright side, connection just look a little slow, and no timeout, no failures. Developer, for them, they even think that the test is already running. But at the end, they are in a queue. They didn't find a browser yet. Sorry, guys, yeah, that's the truth. But now, there's 2 connections that just finished, existing connections. So now, the next connection in the queue moves straight into browser 1. That's the retry mechanism. So the queue starts to drain in a first in, first out logic until everything is empty and every waiting connection got placed. Nothing was ever dropped or end-to-end tests were successfully executed. So now, next big question, what are we going to do now based on the actual size of the browsers? How many browsers do we actually need? Here's the tension. You need 3 browsers, PR wait, developers are all blocked, and 1,000 browsers. I mean, the AWS build just explode. It starts to become like very challenging to find the right signal. We cannot have a fixed number of browsers. So we need to scale on demand. But demand based on what? We needed a strong scaling signal, and we realized it was already sitting in our solution, the queue itself. At the end, the autoscaler, the blue component, will watch the size of the queue. And right now, we have 3 connections waiting. So our autoscaler, which is managed by Keda, thanks to all the DevOps team that have been involved to help us, we created a mechanism to look at the queue size. And then, based on the queue size, we are launching a new browser. Now, those pending connections will be able to move to the new browser. So if we have in this queue 8 connections, 10 connections, assuming that each browser can take 4 connections, so we'll launch more browsers accordingly. So that's what's happening, but this time the queue is draining thanks to the new browser available. Scale-up worked. Connections were moved to the new available browser. So far, so good, guys, right? But our journey from theory to becoming production ready was far from simple. Everything is paper. Yeah. Our main goal during this whole journey was to minimize flakiness coming from our infra. Infra errors are test agnostic. They don't care about your test, what your test does. One infrastructure bug can turn hundreds of tests flaky overnight. On this whole journey surfaced many bugs that we couldn't catch from day one. It was just impossible. So my goal here is to show you all the observation, all the bugs that we saw. And it was like really, really interesting because it was touching all the different layers of our architecture. Let's start from this one. Suddenly, connections are randomly disconnected. How is it possible? I just show you like we have like a good working architecture. It was in the Kubernetes layer. We didn't know, but some connections were randomly dropping in the middle of a test, and it was really hard to catch. No generic timeout error, no clear error message. And what was happening was really, really interesting. Imagine that we have here high traffic, so we have a lot of browsers that are launching, and then we don't have this traffic. Okay, developers are working in the morning, and then they are like starting to get back home, so now we need to reduce the amount of browsers, so we need to find a browser to kill. We cannot like just leave those browsers all online. And the Kubernetes just decided to pick any browsers it wants to kill. On those some browsers, there was some active connection in it. So instead of killing the browser which was idle, it just killed some random browsers without taking into consideration what was inside that browsers. So yeah, so 4 test connections got killed in the middle, and the fix was very interesting. I mean, like there is something called in Kubernetes. We use something called pod deletion cost. That influences the deletion strategy of your pods. So in this case, we are just influencing the deletion by saying to our autoscaler, this pod right there are some active connection. Please don't kill it. We cannot force the deletion strategy. We are just influencing it. That's how it works. OK, another observation. This was very interesting, really hard to catch. Network requests inside the browser were just timing out. page not loading. Just imagine, how is it possible that your browsers, everything in local works, but then you put it in remote, in a PR, stop working, pages are not loading. There is the connection go to browsers, but the browser itself, when it go and navigate to a certain page, all the network requests from that browser, not loading. And here, what was the real issue? Our browser pod sits in an EC2 instance. We are touching the lowest level of our architecture. The network bandwidth of this type of instance was 5 GB per second. And it was completely saturated because of the amount of requests. We were hitting the host network machine limits. I didn't know that something like that could really happen. Even AI today is not able to guess this kind of bug. So there was like a real intention to just monitor all of our infrastructure bugs. So we started migrating to network-optimized instance instead. So many assumptions we had along the way start to fall apart, like this one. But our most important assumption was about to be slapped in the face. One morning, our Slack channel just blew up. Thousands of messages. Yeah, I see you smiling. You know why. From every team, not just one. Developer was saying things like, my tests are randomly failing, is Slack dead, I can't merge my PR. Basically, every pull request at Wix was blocked. And the errors didn't help us. Just connection refuse, timeout, nothing we could really debug with. It was like horrible morning. And I was sick, to be honest, so yeah. But usually, every morning, we go to our monitoring dashboard. The first thing we look at was the pod memory graph. Here's how normally it should look like. 4 connections per pod, as we saw. Each one uses 1 GB, so the pod is roughly around 4 GB. Everyone gets a fair slot. That's the assumption we'd be relying on for months. And suddenly, one morning, we saw this. One single connection was eating several gigabytes of memory, way more than we would ever plan for. That one connection was taking more than the whole pod budget, just for itself. So we asked ourselves, what changed this morning? One thing, a new artifact has just been deployed. It was our brand new editor, Wix Harmony. Yeah, guys, for context, okay, Harmony was about to launch in a few days. Super Bowl ads was already booked. Team was under a lot of pressure. And now their CI is turning red because of end-to-end tests. Fantastic now. So yeah, the pod just couldn't handle it, out of memory killed. Here's the part that really made it really painful. It didn't only kill the Harmony connection, it killed all the single connection that was sitting in this pod. So other tests from the classic editor, viewer, dashboard, innocent test, just taken out by one heavy neighbor. Yeah, we were loading the Wix Harmony editor, it's like a heavy operation. So this wasn't happening on just one pod. It was happening across a whole fleet. So yeah, basically every developer at Wix were blocked by this bug. So Harmony connection were silently stealing everyone else's memory. So we did a trade-off. Any team under fire does this one. We just shrink our max connection to 1 GB, to 1 connection per pod instead of 4. 1 connection, 1 pod. If something dies, it only kills itself. And why it's a trade-off? Because it's come with a real cost. We need almost twice as many pods now. More pods, more money. So that's not a real solution. But in the future, we'll build a smart routing mechanism that will look at the resource needs of each artifact. So if I see Wix Harmony, I will give him a stronger pool. That's what we are going to implement in our roadmap. But now, guys, we are all waiting for the results. So here are our results. You guys will be impressed, I hope. 30% decrease in average end-to-end execution. Faster developer feedback for every developer at Wix. A 60% decrease in infra costs. That was our primary goal, yeah. And we just did it. And just to finish now, by solving our problem, we realized something interesting. Browser hosting is useful way beyond end-to-end testing. Things like bot automation, AI-driven search, web scraping at scale. We realized we built an infra that actually solved a bigger problem than the one we started with. I will finish with one lesson from this whole journey. You cannot know everything up front. At the end, that 1 gigabyte assumption, yeah, we guessed it, we shipped it, and it was wrong. So we need to create a work culture that allows us to infer the unknown. At the end, it's small iteration of build, measure, learn. And here's my point. AI can help us build faster than ever. Okay, whole system in days, not months. But AI can tell you what you actually break when the real users are hitting your productions. That part, it's on you. So do not, please, do not outsource judgment to the machine. And that's how we train our dragon. Thank you, guys.